All right, so we are talking about combustion today. If you have not watched video 6.1, please stop this video, go watch 6.1, and then come back and start watching this. So this is a really quick recap of what you saw in 6.1. So in order to have combustion, you need a fuel and an oxidizer. Typically, the fuel that we'll talk about in this class would be hydrocarbon fuels, so they're made up of carbon and hydrogen. The oxidizer is typically the oxygen and air, but you can use just pure oxygen. Um, Dry air, it's made up of 79% nitrogen and 21% oxygen. So those, clearly there are other gases in there as well, but those are the primary ingredients or components in that mixture. The way that we get that is per 4.76 kilomoles of dry air, right? So both components, really all components together, there is 1 kilomole of oxygen, and that would give you 0.21. So that's where the mole fraction comes from. So why we choose that 4.76 number on the very bottom? Well, this comes from this very general simplified reaction for a hydrocarbon fuel undergoing complete combustion with a theoretical amount of dry air. So the theoretical amount, so this is the minimum amount of air that's required for complete combustion. So it's that stoichiometric amount of air. So we'll be doing a lot of chemical reaction mole balances. So it'll be sort of a flashback to chemistry. And then of course this is dry air, so you don't have any water vapor, and we'll talk about what happens if we do and how we deal with that. Um, so where that 4.76 kilomoles of dry air comes from is this is the air component. This ATH represents that theoretical air, the number of moles of theoretical air. And it's actually going to be the theoretical air times 4.76 kilomoles of dry air. So it's the 1 kilomole of oxygen plus 3.76 kilomoles of nitrogen. Um, We also talk about things in terms of excess air or percent theoretical air. So if you use excess air, as opposed to just the stoichiometric amount of air, the minimum amount of air that you need for complete combustion. Um, so you could refer to that as 50% theoretical air, or you can call this 150% theoretical air, right? Because that's 100% theoretical plus 50% excess. So same kind of logic. 200% excess air would be 100% theoretical air plus 200% excess air. So that would be 300%. And you would call this, by the way, you would put a 1.5 in front of that ATH in your chemical equation. So here you would put a 3 in front of that ATH. 0% excess air, that's just 100% theoretical air, so it's just ATH. If you do use excess air, you're going to have another component over here. There we go, that's what I wanted. And you'll have, in addition to the three products of complete combustion of hydrocarbon fuel with a theoretical amount of air, you'll also have oxygen. So complete combustion with a theoretical amount of air give you carbon dioxide, water, and nitrogen. And then if you have excess air, you'll also have hydrogen. So I think what I'd like to do now, let's go ahead and solve problem 1. So we've got a 10 grams of propane, burns with just enough oxygen. So this is a little bit different. It's not the exact scenario that we just mentioned. Here, our oxidizer is pure oxygen. So let's kind of look at what we've got. So we've got if we had complete combustion with yeah, let's look at that guy. Oh, actually, so let's bring this. All right. So it's going to follow this chemical equation. But instead of having nitrogen here in our oxidizer spot, that's not going to be there anymore. And of course, you won't have any nitrogen here either. So what it's going to look like is you've got your C3H8 plus some amount of oxygen. That's going to give you some amount of CO2 plus some amount of water. So let's go ahead and do the math on that. So we need to do a mole balance. So yeah, let's do that. So mole balance, I don't like that. Let's make this darker. All right, so do our mole balance. And we're going to do it on each element here. So I've got carbon, hydrogen, oxygen. All right, so I've got 3 carbon on the left-hand side. I've got X on the right-hand side, so X is 3. For the hydrogen, I've got 8 on the left-hand side and 2Y on the right-hand side. So, right, you got a 2 there. So that's why you have that Y. And then for the oxygen, I've got ATH, oops, and I almost forgot that 2 there. So it's going to be times 2 on the left-hand side, and then on the right-hand side, I've got 2x plus y. So, of course, y is equal to 4, x is equal to 3. So the number that goes in front of that oxygen is going to be 5. Okay, so here's my balanced equation. Okay, so I've got C3H8 plus 5 times my oxygen yields 3 CO2 plus 4 H2O. All right, so that is my kind of balanced chemical equation. That's not my answer, but I'm going to highlight it because I'm going to continue to refer back to it. So the problem is asking me for the mass of the oxygen that I need for combustion of my C3H8, my 10 grams of C3H8. So I've got this equation written in terms of moles. So it would probably be a really good idea for me to get things in terms of moles and not mass. So all right, so I have 10 grams of C3H8. And remember, my magic number to go between mass and moles is going to be my molar mass. So let's go look up my molar mass. This is going to be in table A1. So there we go. So we have propane. There we go. So 44.09 is my molar mass. Let's go ahead and get that there. So it's well, I would say kilograms per kilomole, but let's put it in grams per mole. Um, all right, so it's going to be divided by, right? So divided by my molar mass. So my molar mass, again, 44.09 grams per mole. And that's going to give me my number of moles. Right, so now this guy All right. And maybe I want to actually get a number for that. Let's do that. So I've got 10 divided by 44.09. Right, so I have 0.2268, and this is moles of C3H8. All right. Of course, I'm looking for grams of oxygen. So, all right, well, let's see how I can relate this to what I've got up here. So I know per 1 mole of C3H8, I need 5 moles of oxygen. So let's start there. So I need 5 moles of oxygen per 1 mole of C3H8, right? So I'm going to multiply by 0.2268 moles of C3H8, and I can see that's going to give me the number of moles of oxygen, but I don't need moles, I need mass, right? I need the mass of oxygen required for this. So for that, I need my molar mass. So for oxygen, go back to table A1. There we go. 32 kilograms per kilomole, which is the same thing as grams per mole. So let's go ahead and put that there. So I got 32 grams of oxygen per mole of oxygen. Right? And so all that should give me the grams of oxygen, and I've got 36.29 grams of oxygen. Perfect. Awesome. All right, so let's go to problem 2. All right, so here we have a gas turbine burns octane, so C8H18 completely with 400% theoretical air. So you'll see I went ahead and I put in here that I've got 400% theoretical air, and I know that's just 4 times ATH. And I want to find the amount of nitrogen in the products in kilomoles per kilomole of fuel. So that's a little bit strange, but once we get our balanced equation, you'll see a little bit more, it'll be a little bit more obvious about what we're looking for here. All right, so let's go ahead and put this here. So the first thing that we want to do is we want to get our balanced equation. Um, yeah. And there are 2 steps that are needed for this. So first thing is we need to find the minimum amount of air that's required for this. So what we're going to do is we're going to get the balanced equation for complete combustion of C8H18 with just 100% theoretical air. So, yep, we're going to ignore that 4, and we're going to write, I've got C8H18 plus ATH times O2 plus 3.76 nitrogen, and that's going to yield some amount of CO2, some amount of H2O, and some amount of nitrogen. So what I need to do is do my mole balance again. So let's go do that. So on my carbon, so I've got 8 on the left-hand side, I've got X on the right-hand side. For my hydrogen, I've got 18 on the left-hand side and I've got 2Y on the right-hand side, so Y is equal to 9. For my oxygen, I've got 2 ATH on the left-hand side, and I have on the right-hand side, I've got 2X plus Y. So my ATH, let's see, ATH ends up being 12.5. And so that's it. I don't even have to solve for that last Z value. It doesn't matter. Now I'm going to plug in that ATH into the equation with excess air. All right. So what are we going to get? We are going to get I've got C8H18, but now instead of just writing ATH, I'm going to write 4ATH times O2 plus 3.76 nitrogen. That's going to give me some amount of CO2, some amount of H2O, some amount of nitrogen, and I've also got some amount of oxygen. So remember, you have to include that last term because, again, we do have excess air. All right, so I told you that it would be a little bit more obvious once we started looking at this about what they're actually asking for. So they're asking for the amount of nitrogen, the number of moles of nitrogen per number of moles of fuel. So it's really the parameter that we're looking for is Z, right? Because Z is the number of moles of nitrogen per 1 mole of C3H18, right? There's an implied 1 in front of that C8H18. So this is per 1 kilomole of C8H18. So that's what I'm going to do. So I'm going to do my mole balance, but I'm going to keep in mind what I'm really after is Z. All right, so for my carbon, 8 on the left-hand side, X on the right-hand side. For my hydrogen, I got 18 on the left-hand side and 2Y on the right-hand side. For my, oh, actually, I really don't need any of this other stuff. All I need is Z, isn't it? Or don't I? So let's go ahead and get Z. Z, it looks like if I do my mole balance on that nitrogen, yeah, I'm going to cross that out because I don't even think I need it, do I? So my Z, the number of moles, yeah, let's do this. So mole balance on my nitrogen. I have 4 times my ATH. What's my ATH? My ATH is 12.5. So 12.5, 4 times 12.5 times 3.76 times 2, right? Got a 2 there. Equals 2 times Z, because I've got a 2 over here on the right-hand side. So it's just a matter of solving for Z. So Z is going to be, well, these 2's are going to cancel out. So 4 times 12.5, so that'd be whatever 50 times 3.76 is. And those units are going to be, it's kilomoles of nitrogen per 1 kilomole of C8H18. And that is what we're looking for there. All right, so let's move on to problem 3. All right, so we have C12H26 burns completely with 150% theoretical air, and we want to find some stuff. So we want to find the air-fuel ratio on a molar and a mass basis, and then we want to find the dew point temperature. So, okay, let's look at that. So air-fuel ratio is just what it sounds like. It's the ratio of dry air to fuel. So looking on the reactant side. So clearly, I'm going to need to know the balance, the balanced chemical equation here. So that is the first thing that I'm going to do. Get my balanced equation. All right. So first things first, I got to find ATH. Okay. Because I've got 150% theoretical air, but I don't know what that theoretical air is. So I need to balance the equation just with that theoretical amount of air, just with that stoichiometric amount of air, and figure out what that ATH is. So I have C12H26 plus just that ATH times O2 plus 3.76 nitrogen, and that's going to yield some amount of CO2, some amount of H2O, some amount of nitrogen. All right, so again, it's just a mole balance here. So carbon, I've got 12 on the left-hand side. I've got 2x. Yeah, see there's a 2 right there. 2x on the right. I'm sorry, just kidding. That's a lie. Not doing a mole balance on the carbon or the oxygen, do it on the carbon. So there we go. So X is 12, right? Let's do it for our hydrogen. So we have 26 on the left-hand side, and there we go. Now we're doing 2Y on the right-hand side. So 14 is Y. Um, and then let's do for the oxygen. So I've got 2 ATH on the left-hand side, and then I've got 2X plus Y on the right-hand side. So my ATH for this guy ends up 18.5. Perfect. So now I need to get my balanced equation for 150% theoretical air. All right, so let's do that. All right, so I have C12H26 plus 150% theoretical air, so 1.5 times that theoretical air, which is that guy right there. So it's going to be 18.5 times O2 plus 3.76 nitrogen, and that's going to give me some amount of CO2, some amount of H2O, some amount of nitrogen, and some amount of oxygen. And I don't want to forget about that guy. I'm just going to put the go. All right. So another mole balance, and then we'll have our chemical equation. So for the carbon, 12 on the left-hand side, X on the right-hand side. For the hydrogen, 26 on the left-hand side and 2Y on the right-hand side. Y is still there. Oh, I don't know. I realized somebody was probably screaming at me. Whoopsies. Yeah, 26 divided by 2 is not 14, it's 13. Okay. ATH is fine. But yeah, that was just a sorry about that. All right, and then we've got oxygen, so let's do that. So I have, ooh, did I do that oxygen? Okay, I'm sorry, I was like, ooh, did I forget something in a previous problem? I was all of a sudden second guessing myself for everything then. All right, so for my oxygen, I have, on the left-hand side, I have 1.5 times 18.5, which is my theoretical air, times 2, right? Because there's a 2 there. And then on the right-hand side, I've got 2x plus 2w. So yeah, my w, let's see what he ends up being. W ends up being 9.25. So we're all good there. And then the only other thing I guess that I do need things for my nitrogen. So I could do my mole balance on my nitrogen. You know, in the previous problem, I just did it on nitrogen without the little subscript 2. I'm going to do it with the subscript 2. It doesn't really matter, but just less stuff to write down, I guess. So let's see. So that means on the left-hand side, I got 1.5 times 18.5 times 3.76. I'm not multiplying it by 2 because I'm just doing the mole balance on that diatomic nitrogen. And then this is equal to just Z, which Z ends up being 104.34. All right, so my balanced equation in all of its glory, so I've got C12H26 plus, and this ends up being 27.75 times O2 plus 3.76 nitrogen. And then that's going to give us 12 CO2 plus 13 H2O plus 104.34 nitrogen plus 9.25. I don't know why I'm continuing to color code that, but I am. 9.25 oxygen. All right, so what I'm going to do now, I'm just going to kind of highlight that because we'll be referencing that. It's not our answer, but definitely going to be referencing that because that's my final balanced equation there. All right, so what I was supposed to find the air-fuel ratio. So the first one is in terms of, well, it doesn't really matter. So one's on a molar basis and one is on a per mass basis. So the one that is on a mass basis is like that. So it's the mass of that dry air over the mass of our fuel. All right. And I've got this lovely chemical equation just written in terms of moles. So let's relate that to the moles. Um, so let's see. So this would be the number of moles of air times our molar mass of air. That would give me mass, right? And then the number of moles of fuel times our molar mass of the fuel. Can I spell fuel? I don't know. Okay. All right. So the number of moles of air. So I am looking at this little section right here. So remember in the parentheses, that represents 1 plus 3.76 moles, so 4.76. I'm going to put it in terms of kilomoles. So there are 27.75 times 4 or 0.76 kilomoles of air per 1 kilomole of C12H26. So I think, you know, I've got things in terms of moles now, don't I? Times, then I've got the ratio of the molar masses. So the molar mass of my air, I can look this up in table A1, but I probably remember it, 28.97 kilograms per kilomole. So of course that's going to cancel out, or at least the kilomoles are going to cancel out. And then the molar mass of my C12H26. Normally I would say, let's go look that up. But unfortunately, I don't think I have that. Yeah. So, uh-oh, what do we do? This one, it's not too bad. So it's not in table A1. But that's okay. We can calculate it. So it is in our, so we got C12H26. So it is C12H26. So this is going to be, I've got 12 carbon, and our molar mass of carbon is 12.01. So there's our carbon, and then when we get to it, where's our hydrogen? Somewhere on there, right? Uh, One would think. Oh, I see it. I see it. I see it. Of course, it's H2, so really, one hydrogen would be 1.008. Yeah. So, all right. So for the carbon, I've got 12 carbon with a molar mass of 12.01 kilograms per kilomole, plus, and I got 26 of my hydrogen, so 1.008 kilograms per kilomole. All right. And so I end up getting 170.328 is a point. Ah, it's terrible. 100 and there we go. Having 170.328. And this is kilograms per kilomole. So 170.328 kilograms per kilomole. Perfect. And so this ends up being 22.47, and that is kilograms per, well, just kilograms per kilogram. So it's kilograms of dry air per kilogram of your fuel. All right, so I guess that's one of the things that we're supposed to find. And of course, this right here, you'll notice this is going to be in terms of kilomoles of dry air per kilomole of fuel. So boy, isn't that going to be useful. So that is exactly what our air fuel ratio is with a little bar over it. So on a molar basis, it's just the number of moles of air per, per number of mole of, right. So this ends up being, whatever 27.75 times 4.76 is, right? That whole thing. Yeah, might as well just, there we go. But this is going to be in kilomole of air per dry air per kilomole of fuel. Right. And unfortunately, that wasn't the only thing that we needed. We needed the dew point temperature of the products. Okay. So part B, we need dew point temperature. And what we're talking about is, we're talking about the temperature at which that water, at which it says the dew point temperature of the combustion products, but the only thing that's going to condense at any normal temperatures is going to be water. So that's what we're talking about there. So it's the dew point temperature of the water in the products. Okay. So again, we're going to be referencing that balanced chemical equation. So C12H26 plus 27.75 times O2 plus 3.76 nitrogen yields 12 CO2 plus 13 H2O plus 104.34 nitrogen. Oh my goodness, plus 9.25 oxygen. I did not realize that I was going to be running out of room here, so I'm going to have to. Oh, I. Oop. All right, hold on a second. I think I. Hold, please. Okay. Sorry for that. Okay. So, all right. So, yeah, so here's my balanced chemical equation, and I am looking at the dew point temperature of the water in the products here. Let's make that actually look like an oxygen there. All right, so remember our dew point temperature and how that was defined, and we defined that in the previous chapter. So that dew point temperature, TDP, and again, we're looking at the products, but this is going to be the saturation temperature at the vapor pressure of that water. Again, talking about products. Right? And so I need to figure out what that vapor pressure is. Well, for Dalton's model. So what did Dalton's model say? Well, it defined those partial pressures. So PV, again, we're talking about the products as a function of our mole fraction times the overall pressure. And of course, we are talking about, not to harp on it too much, but it is in the products. All right, so the overall pressure, so it says, and if we look at the problem statement, it says the dew point temperature of the combustion products when cooled at 1 atm. So our pressure here would be 1 atm. Let's go ahead and put that in terms of I guess we'll put it in terms of bar, because, well, that's what our tables are in. So this would be 1.01325 bar. And then, of course, my mole fraction here. So we are talking about the mole fraction of the water here in its mixture, its ideal gas mixture. So yeah, so this is going to be, it's the number of bowls of water, 13, in the entire thing. And we're just talking about the entire thing. The entire thing is the products. So let's see, so I've got 12 plus 13 plus 104.34 plus 9.25. There we go. So I end up getting a mole fraction, let's see, of 0.098. And so now I got enough information to get the vapor pressure of the water in the, or the vapor pressure in the products. I end up getting 0.09504 bar. Okay, and remember why I needed that, because I need to get the saturation temperature at that at that vapor pressure. So 0.09504 bar. So I need to go to my saturated tables. I can go to the ones organized by temperature or pressure. That's pretty small. I think if I go to the ones that are organized by pressure, I'll have to extrapolate, but let's just see. So if I go to table A3, the lowest pressure that I've got is 0.04. Actually, it's fine. So yeah, so we're looking at 0.09504. So I end up getting, it's in between 41.51 and 45.81. I actually ended up interpolating into A2 because I get a little bit narrower range there. But yeah, I got 44.8 if I interpolated in table A2. Let's just go ahead and round it off to 45. Yeah. So this is going to be TSAT at 0.09504 bar, which is about 45 degrees Celsius. All right. Perfect. All right, so let's do another one. All right. So problem 4, we have hydrogen. So not a hydrocarbon fuel, just pure hydrogen enters a combustion chamber, combustor, with a mass flow rate of 2 kilograms per hour, and burns with air exiting or entering at 30 degrees Celsius. So okay, so let's figure this guy out. So let's come back to him. Reason I'm saying come back is because this guy right here has hydrogen and not a hydrocarbon fuel, and I suspect that we may be you're more likely to get something with a hydrocarbon fuel on the exam. So let's just kind of, we'll put a pin on that. We'll come back to it maybe if we have time. All right. Problem 5, we have butane, C4H10, burns completely with 160% theoretical air, entering at 20 degrees Celsius, 1 atm, 90% relative humidity. So this is kind of interesting because we have a relative humidity of 90%, which tells us that we have moisture in the air. So we kind of have to be very careful when we get our balanced equation. So let's start working it. Okay, so we want to find the dew point temperature again of the water in those products, and got a little bit similar to the last problem in that we have excess air, but dissimilar in that we have water within the not products but reactants. All right, so we got to get our balanced equation. Let's get that. So I'm going to bring it up here. All right, so our balanced equation. All right, so let's go ahead and get our ATH. So, and I think, yeah, let's go ahead and at least let's write this out. So I've got C4H10 plus, see, I've got 1.6 ATH times O2 plus 3.76 nitrogen plus, got something else because I've got relative humidity, so I know that I've got some amount of water within that air. So it's not just dry air, we've got water too. So we got moist air coming in. So, and I'm going to call that coefficient B. So some amount of water. And then that's going to give us, I'm going to give us some amount of CO2, some amount of H2O, some amount of nitrogen, and some amount of oxygen. So I don't want to forget him. All right, so that's my balanced equation. So the first thing that I need to do, and actually let's make this a little lighter. First thing that I want to do is I want to find ATH. All right. So for this, I need to balance the chemical equation with just the stoichiometric amount of air. So let's do that. So I have C C4H10 plus ATH times O2 plus 3.76 nitrogen yields some amount of CO2 plus some amount of H2O and some amount of nitrogen. Notice that I did not include that excess oxygen, and I also did not include the water in the reactants. So I will let you do your mole balance because it's very, very similar to what we've done before. Same mole balance. And the important takeaway message is that your theoretical air ends up being 6.2, I'm sorry, just 6.5, not 6.25, 6.5. So what I'm going to do here is I am going to, I think I'll kind of highlight that because that's going to be that guy right there. Alrighty, next thing, I got to plug in that theoretical air. So let's go do that. So I have, if I plug in that theoretical amount of air into my chemical equation up here. So let's do my mole balance. So need to do it on my carbon, my hydrogen, on my oxygen, on my nitrogen. I think that's it. All right. So for the carbon, on the left-hand side, I have 4. On the right-hand side, I have X. That was easy. Let's do it for the hydrogen. So for the hydrogen, I have 10, but then I've also got the little blue BH2O that I got to deal with. So let's not forget him. So I've got 10 plus 2B, right? And then that's going to equal, on the right-hand side, I've just got the hydrogen in the water. So it's going to be 2Y. So in other words, 5 plus B is equal to Y. Okay. So I've got one equation and 2 unknowns. Maybe it's not an issue yet, but let's see. Now let's do it for our oxygen. So for my oxygen, I have 1.6 times ATH. My ATH was 6.5. So let's color code here. Times 2 plus, and I don't want to forget, I do have a B term there, so let's not forget about him. And then this is going to be equal to, let's see, so on the right-hand side, I have 2x plus y plus my w. Yeah, that's actually, it's 2w, isn't it? 2w. All right. And actually, before I kind of bring that nitrogen down in a hot second, um, so I think maybe what I'll do now is let's take, since I've got a W, I've got an X, which I know him, right? He's 4, so that's fine. Let's go ahead and put that 5 plus B is equal to Y and see what we get. So I have, if I do the math for this 1.6 times 6.5 times 2, that's going to give me, let's see, uh, 20.8. 20.8 plus B equals 2 times X, which is 4, plus Y, which I'm saying is 5 plus B plus, this is a 2W. All right. So I don't know, that doesn't really help me with B, but it does help me with W, I guess. So W ends up being 3.9, right? Yeah, that's all I got. Yeah, yeah, yeah. All right. So I don't know. Let's highlight that W. That one got him. Um, X got him. Uh, Y. Oh, now I need a Y. I haven't gotten Y, have I? Yeah. And Z. I guess I can get Z. That's not too bad. Um, yeah. So let's do our mole balance on our nitrogen. So I've got 1.6 times 6.5 again. Okay. Times 6.5 times 3.76 times 2, which is equal to 2Z. So anyway, I get a Z value of 39.104. Okay. Okay, great. I don't know. Let's put him as green, I guess. So yeah, I got that one at least. So I'm pretty good. The only unknowns that I have or that I need to get that my mole balance didn't really help me with is B and Y. All right. So here I'm going to look to my relative humidity because I haven't really used him yet. So let's do that. So I'm going to use my relative humidity, which is 90%, to help me get B. So how is that going to help me? Well, that relative humidity, it describes, um, it refers to, or it describes the um, it's not the ratio, but it relates the dry air and the water component. So let's kind of think about that. So our relative humidity, it's defined as P sub V over P sub G, right? And we're looking at, this is of course, and the reactants, right? Right, the moist air. So let's kind of think about what that moist air is. If I look at this guy right here, all of this, that's that atmospheric moist air. All right. So I know that this is 90%. I could probably figure out that PV. The P sub G is the Psat at whatever the temperature is for that moist air, which I see is 20 degrees. So yeah. So where E sub G is equal to P sat, and it's at the temperature of that moist air, which is 20 degrees Celsius. You can look this up. I have got 0.02339 bar. And again, I can get this in table A2. So I get a PV value, and this is I'm again looking at just looking at the moist air. So the partial pressure of the water vapor in that moist air, so in that moist air, ends up being 0.9 times 0.02339 bar, which is equal to 0.021051 bar. So how does this help me? That is again, this is the vapor pressure of, yeah, it's fine. It's the vapor pressure of the water in that moist air. And I know that that is equal to the, it's equal to the mole fraction times the pressure. And again, it's for the moist air. I keep on harping on the fact that it's the moist air because we're going to define that mole fraction for that moist air. All right, so the mole fraction, let's go ahead and get that. And then of course the pressure. It said everything's coming in at 1 atm, so let's put this in bar, 1.0125 bar. All right, so let's look at my mole fraction here. All right, so I need to give myself a little bit more room, so forgive me. I'm going to erase this and then I'm going to come back to it. So the mole fraction, the number of moles of water per number of moles in the entire mixture. So number of moles of water in that moist air, right? In that moist air is going to be B over, and I have 1.6 times theoretical air, 6.5 times, now I've got O2 plus 3.76 nitrogen. This is 4.76 kilomoles of dry air plus B. So that is that mole fraction of the water in the moist air. Now I've got to multiply it by the pressure. So my pressure again, 1.01325 bar. And then I end up getting a partial pressure, or I'm sorry, I know that this is all, I'm sorry, not looking for the partial pressure. I already calculated the partial pressure. I know this is 0.021051 bar. And I am trying to solve for the only unknown in that equation, which is B. So it is going to take some rearranging on your part. It's just algebra. So I won't do it here, but I end up getting 1.0503. And remember that my y is equal to 5 plus b. So it's going to be 6.0503. All right, perfect. And now what was I looking for? Because I almost forgot. I'm supposed to find a dew point temperature here. So let's kind of recap. So I've got my balanced equation. That was a lot of work to get that balanced equation, but I got it. So I've got C4, H10 plus, I got 10.4 times O2 plus 3.76 nitrogen. Right, so that's that 1.6 times times 6.5 plus B, which is that 1.0503, that blue, H2O, and that's going to yield, let's kind of bring it down to the next line, it's going to yield 4 CO2 plus 6.053 H2O plus our Z value, which I've already got. So my Z value is 39.104 nitrogen plus our 3.9 oxygen. All right, so that's my balanced equation. I'm good to go. I'm supposed to find, I need the dew point temperature of the water in the products. So what are my products? My products are all these right here. So when I'm talking about, when I define mole fractions or anything like that, it's that mixture, it's that product mixture that I'm talking about. So I'm going to do the exact same sort of methodology that I did on the previous problem where I calculated the dew point temperature of the water in the products. I know that this is equal to T sat at PV in the products. So I need to figure out what that PV is. So our PV in the products, it's equal to the mole fraction of the water in the products times the pressure of the products. And we said that everything's exiting at, this guy is at 1 atm, 1.01325 bar. And so I do need to figure out the mole fraction. So let's do that. So the mole fraction of the water vapor in that product, or in the products there. So the whole mixture is what's highlighted there. So it's the number of moles of water, 6.053, over the total number of moles in the mixture, which is 4 plus 6.053 plus 39.104 plus 3.9. And so I end up getting, well, I tell you what, I don't actually know what I get for that mole fraction. I don't have a number there, but I do have a value for that partial pressure, which is 0.115551 bar. And so the saturation temperature at that vapor pressure, let's go look and see about what it is. So 0.11555 bar. All right. So actually, I'm going to look in A2 because I think probably and get a little bit closer. Yeah. Oh, well, that's slightly annoying. So 0.115551 bar, and I'm looking for the saturation temperature. And then the next one I've got down here, I'm just going to copy right here, 50 and 0.25 bar. So it's between 45 and 50. I mean, looks a little bit, it's probably about 47, 48 degrees Celsius. So it's about, we'll say 47 degrees Celsius. And you're looking in table, I looked in A2, but you can look in A3 as well. Right. And there's a couple more practice problems sort of like this. So I would encourage you to check those out. Should be on the YouTube playlist. Okay. All righty. So next thing we are going to look for combustion. Yes. So I want to at least, we're going to work through one problem. I'm going to grab a drink of water. So I'm going to pause the video shortly. All right, so if you have not watched video 6.2 yet, I would suggest that you do. So this talks about the first law of combustion applied to open systems. We also have a first law for closed systems, but in this class we are going to limit our discussion to open systems. So let's kind of look at we won't go over the derivation, but this is what we have. Yeah, so see, let's look at the more drawn out equation here. So Yeah, I've got some we define those H bar terms, but they're a bit more in depth there. So here's our first law. For an open system, we will not work with closed systems. We will not deal with systems that have power. It's just going to be a Q dot term. So rate of heat transferred per uh, molar flow rate of fuel. So that'd be kilomoles per second or something like that. Um, these values right here, these N values, those are going to be the coefficients that are in front of the products and reactants in your balanced chemical equation. These values right here, this H naught F, those are enthalpy of formation values. So these are values that you can actually look up for common substances. These are found in table A25 and A25E. They're also found for some gases in A23 uh, at the top, and I'll show you in just a second. These values right here are the H bar values. So it's got a bar over it, so it's per unit mole. So kilojoules per kilomole, say. These are evaluated at the given temperature. And really, honestly, it doesn't really matter what pressure it's at because enthalpy, it's only dependent on the pressure. But it's the H bar value for the gas that you're interested in at whatever, whatever temperature that gas is coming out at for the products or going in at for the reactants. And you can look this guy up and we'll see. We'll look that up for A23 and A20. And then the very last one, it's a little H bar naught. This is H bar, but it's evaluated at standard reference temperature, so at 298 Kelvin, or if we were in English units, 537 degrees Rankine. So I think it's probably more helpful to just solve a problem and see how all of these terms come together. So let's go do that. Alrighty. So we have liquid octane C8H18 at 77 degrees Fahrenheit. 1 atm enters a combustion chamber operating at steady state and burns completely with 50% excess air. So you can see 50% plus 100% dry air entering at 120 degrees Fahrenheit. 1 atm. Everything is exiting at 160 degrees Fahrenheit. I am not going to do this second part. So we are only going to look at case A. I don't even call it case A because it's the only thing I'm looking at. But we're going to look at Q dot for if our products are exiting at 1060 degrees Fahrenheit. And I'll tell you why we're not going to look at 537 degrees Rankine or 77 degrees Fahrenheit, right? Same thing. All right, so I'm trying to find the Q dot over N dot of our fuel. So first things first, get your balanced equation. So let's do that. So our balanced equation. So number one, first thing, find ATH. So I've got C4H10 plus ATH times O2 plus 3.76 nitrogen. And that's going to yield some amount of CO2 plus some amount of H2O plus some amount of nitrogen. So let's just kind of fill in the blanks here. So I have this one's got to be 4. My cat's here. Don't mess up anything. Love you, kitty, but no. So that's got to be 4. For my hydrogen, looks like this is going to have to be 5. And so if I want my ATH value, it's like ATH is going to have to be 12.5. Yeah, I'll put it as, yeah, 12.5. All right. So now, got to plug in ATH, plug in that theoretical air. So we have C4H10 plus, and I've got 1.5 times that theoretical air times O2 plus 3.76 nitrogen. And then that's going to give me, I'm going to have CO2, water, nitrogen, and then oxygen. So I'm just going to put some blanks here, save myself a little bit of room, try to be as efficient as possible. All right, should have really not written that small, but okay, whoops. All right, so it looks like this has got to be 4. For the water, this has got to be 5. For the nitrogen, it's going to be 1.5 times 12 times 3.76, which ends up being 70.5. And then for the oxygen, it ends up, so it's going to be 1.5 times 12 times 2 minus 2 times 4, all divided by, minus 5, all divided by 2. So it's going to be 6.25. All right. So what I'm going to do here is I am going to just kind of highlight this because I have a feeling that I'm going to be referencing this. So let's just kind of color all the stuff in. All righty. Okay, so now I'm going to be looking at my first law applied to a chemically reacting system, right? So I have I'm going to copy directly from my equation sheet, and I'm going to ignore the W dot term, and it's just going to give me dot over N dot of my fuel. So I'm looking that equation down there at the bottom. That's what I'm writing. So this is equal to, and I'll have the sum, and it's going to be the products minus the reactants. So number of moles of product times, it's going to be the enthalpy of formation, plus the enthalpy at the temperature of those products. And the temperature of those products, they tell us, is 1060 degrees Fahrenheit. So 1520 degrees Rankine. So I'm going to just kind of make a note of that. My products are coming out at 1520 degrees Rankine. That's what I'm evaluating it at. Minus the enthalpy at standard reference state. And actually, I like writing it, I don't know why I just wrote it like that. I'm going to look this up. I'm going to put a little subscript. I like it. I like the way that looks better. So this is at 1520 degrees Rankine minus the enthalpy at standard reference state. Standard reference state is 537 degrees Rankine, 77 degrees Fahrenheit. It's room temperature. So 537 degrees Rankine. So all my products are coming out at that. Now I look at my reactants. So I kind of got to be careful here because I've got two different temperatures. I've got the temperature of my fuel, and then I've got the temperature of the air. So I've got two different temperatures there, so I can't write it as nicely and neatly as I would like to, just in this kind of this equation right here where I'm not plugging in numbers quite yet. But I'll just kind of make a note. This is the number of moles reactant. This is the enthalpy of formation for each of those reactants, plus the enthalpy at whatever temperature that those reactants are coming in at. I'll deal with that in a second. Minus the enthalpy at standard reference state. Standard reference state is always the same. It's 537 degrees Rankine. All right. So we're going to handle the products first, and bear with me because I'm going to need to sort of go back and forth, and I'm going to show you where these things are. So we're looking on the product side, and I see that I have 4 products. So I've got CO2, I've got oxygen, I've got nitrogen, and I've got oxygen. So let's make a note first. So I'm going to put some placeholders here. So as I'm flipping back and forth, well, it'll minimize the flipping back and forth. How about that? All right. So the number of moles of product, and it's number of moles of product per mole of fuel, but per one mole of fuel there. So, all right. So the first one is going to be, I have 4, I'll put it as kilomoles of CO2 per kilomole of C4H10, right? And then all of these H bar terms are going to be in terms of kilojoules per kilomole of CO2. So you can see that it's going to, this whole term is going to break down to kilojoules per uh, kilomole of fuel, right? Which is what we want. All right. So I need my H bar, my enthalpy of formation for CO2, and need some H bar values. So yeah, all of this is going to be, that's going to be in kilojoules per kilomole of CO2. So I'll just write my placeholders for now. And then I've got the water term. So the water term is next here, right? So I have 5 kilomoles of water per kilomole of C4H10. And all those H bar values that I'm going to look up are going to be in kilojoules per kilomole of water. So you can see that when I cancel things out, of course, all I'm going to be left with is kilojoules per kilomole of fuel, right? Kilojoules per kilomole of fuel. All right. Plus, I got another product there. I've got 70.5 kilomole of water per of fuel C4H10, right? And then I'm going to multiply by a whole bunch of H values here. So this is kilojoules per kilomole of, oh, I'm sorry. This is not water, this is nitrogen. Just got to be patient with me. I'll eventually get there. All right. Of course, that and that cancel out. Bump. Nope, that's left. And then I have one more of those product terms left, and that's the oxygen. So I have 6.25, and it's kilomoles of oxygen per kilomole of fuel, C4H10. And then I've got a whole bunch of H values that I'm going to plug in there. Those are kilojoules per kilomole of oxygen. Ba-dump, dump, dump. All right, so that takes care of all of my products. So I'm all good there. The only thing I need to do now is I need to take care of the reactants. And I have 3 reactants. I've got the fuel, I've got oxygen, and I've got nitrogen. So, all right, so now it's all minus 1 kilomole of C4H10 per kilomole of C4H10. And then I'm going to pass some H bar values, and that's fine. I'll deal with that in a second. All right. See about the next one. So I've got 1.5 times 12. So 12 plus 6, so 18. So I've got 18, and it's kilomoles of oxygen per kilomole of fuel C4H10, right? And then let's see, I've got one more thing. I've got my nitrogen. So it's going to be 1.5 times 12 times 3.76, which ends up being 70.5. So minus 70.5 kilomoles of nitrogen per kilomole of C4H10. All right, oops, did that again. And then I've got my kilojoules per mole. Oh, and I'm sorry, this should not be kilojoules per. Sorry, I was getting a little bit. Oh, that should be C4H10, but this second one should be kilomoles of O2, and this should be kilojoules per kilomole of nitrogen. So you can see again, that guy, that guy, this guy, that guy. Everything's going to give us kilojoules per kilomole of fuel, which is what we wanted in the first place. Okay. Got to plug some numbers into those into those brackets there. So let's handle the first one. So all the products are coming out at 1520. So that should be pretty easy. And I need to get the H bar at 537 values, and then I also need to get the enthalpy of formation values. So I've got four products: CO2, H2O, nitrogen, and oxygen. All of those values can be found in A23. A23. So let's go to A23. And actually, we are in English units, so I probably need to go to A23E. So it's the ones that are sideways here. All right, so you will notice happily that I have values for CO2, water, oxygen, and nitrogen, and all of those are values that I need. So I need, let's see, so for things coming out, oh, I have enthalpy of formation values. I told you you can get them into table A25, and you can. So I'll show you where those are. Yeah. So you do have enthalpy of formation values for other substances as well in A25 E, but since they're kind of listed up here at the top, I think we're good. So we will plug those in. So for CO2, it's going to be negative 169, 169, negative 169 1,300 BTU per pound mole. Oh my goodness. All right. Then I need my H bar at 1520 degrees Rankine because that is the temperature that the products are coming out at. So 1520. So I need to kind of scroll on down here, 1520. All right. So I need it for CO2, water, oxygen, and nitrogen. So for CO2, I'm going to use this value. For my water vapor, this value. Yeah, make this a little bit smaller so I can kind of get that out of the way. So you can see all this is going to be at 1520. All right, perfect. So let's at least get those because oh, and I also need things at 537 degrees Rankine. So let's go ahead and get that. So 537. So 537, here's the H bar for CO2, for water vapor, here it is. For oxygen, here it is. For nitrogen, there we go. So I'm going to write those on my work, but just so you know, that's where I'm getting them, A23. All right. Oh, and you'll notice, fun, yeah, for nitrogen and for oxygen, 0. 0. So that's kind of for the enthalpy of formation. That's kind of nice, isn't it? All right. So enthalpy of formation for the first guy. Oh, and this should be. I'm sorry. This should have an F right here. This is formation. Um, so H bar enthalpy of formation for CO2 is going to be negative. Oops, dang it. Negative 169,300 BT. Oh my goodness. Darn it. Darn it. I need them to be not in kilojoules per kilomole or kilojoules per. Oh my goodness. Somebody is internally screaming, like, pay attention, pay attention. All right. Well, luckily, I can pause it and I'll fix it right now. Okay. Ta-da! We fixed it. All right, so it should not be kilojoules per kilomole. It should be pound mass per or pound mole per pound mole and BTU per pound mole. So, okay. So enthalpy of formation for the CO2, negative 169,300. And at 1520 degrees Rankine, I have 14,824.8. And at standard reference date of 537 degrees Rankine, I have 4,027.5. All right. Now we move on to the oxygen. So the enthalpy of formation, and you'll notice, by the way, that enthalpy of formation is for water vapor. And it's not surprising that it exists as a gas, because usually that's the sort of thing that you do need to figure out, right? Does it exist as a vapor? Well, it's coming out at over 1,000 degrees Fahrenheit, so absolutely it's coming out as a vapor. The reason that I decided we're not going to repeat the process for figuring out what the Q dot over N dot is for if they exit at room temperature, we would have to account for the fact that some of that water is going to condense, and we are sort of in crunch mode, so we are going to ignore that part. If it were a regular semester, we'd have a little bit more time, but we're not going to worry about that now. So in these combustion problems, you can go ahead and take it for granted that anything that's coming out is going to be exiting. If you have to calculate a Q dot, it's coming out as a vapor. Okay, so with that being said, let's go ahead and come back here. Let's put our enthalpy of formation for our water vapor. So this is, oh, I think, oh, shoot. Oh, no, this is, darn it. Darn it, darn it. I messed up on a few things here, and I'm really sorry about that. This is not, yeah, some of you may have noticed. Yeah, so my numbers do reflect C8H18. Some of them do anyway. So let's see. So sorry, y'all. C8H18. My goodness. Goodness. Yeah. So some of these things are gonna change, aren't they? You guys are, it is 12.5, by the way. If somebody had like done the math and they would have figured out, that doesn't make sense. But it does make sense. Oh, guys, I'm sorry. It does make sense if we had the right numbers. Oh, goodness gracious. So this guy would be 8, this guy would be 9, and ATH would be 12.5. Um, all right, so this does change these numbers over here. I'm sorry about that. The last two are fine, but this one needs to be 8. This one needs to be 9. So this is 8. This is 9. I'm very sorry about that, guys. Man. All right. Should have stopped while I was ahead, but we're going to keep on plowing ahead. All right. All right, so the next one, we've got water. So the enthalpy of formation for water vapor, as we see in table A25E, is 100,000, 104,040. Enthalpy at uh, 1520 degrees Rankine ends up being 12,738.8. And the enthalpy at standard reference state at 500, at 537, at 537 degrees Rankine ends up being, let's look. Oh, I'm second guessing myself. Ends up being negative four, ends up being 4258.0. All right. Then we've got, what else do we have? So we have our nitrogen. So enthalpy of formation for nitrogen at the very top, you'll see it's 0 BTU per pound mole. And then the enthalpy at 1520 degrees Rankine for nitrogen. Let's see what he was. Let's make sure we got the right thing. So he ends up being, yep, 10,000, 10,800.4. 100.4. And then at 537 degrees Rankine ends up being 42, oh, sorry, uh, 32, 3729.5. 3729.5. All right, on to oxygen. Oxygen also has an enthalpy formation of 0 BTU per pound mole of oxygen. Enthalpy of oxygen at 1520 degrees Rankine ends up being 11,179,000.6, and at standard reference state at 537 degrees Rankine, up having 3725.1. All right. Let's move away. I'm not going to worry about the fuel right now. Actually, I will. Yeah. So we're at the product side. All right. So you may notice table A23E doesn't have any tables for H bar for fuel, and that's okay. So, but we do have an enthalpy of formation value that we can pull off at A25E. So, yeah, looks like my little wheel go where he went. Oh, there he is. All right. Yeah. So we got two values for octane. We need the one for liquid. We got liquid. There's our enthalpy of formation. So negative 107,530. So let's go ahead and get that. So negative 107,530. And like I said, you may worry because you don't see any H bar values in table A23 for octane, but that is okay because you will notice that the octane, we're talking about the reactants, and that octane is coming in at 77 degrees Fahrenheit or 537 degrees Rankine. And then the enthalpy at standard reference state would be taken at 537 degrees Rankine as well. And so you can see that those two things are just going to cancel out. And for this class, your fuel is always going to be coming in at room temperature. So those terms will cancel out. Just make sure you understand why. All right. So our oxygen and our nitrogen, our air, remember our air is coming in at 120 degrees Fahrenheit. So 580 uh 20. Oh, sorry. Yeah. 580 degrees Rankine. So I do need to get those values. So yeah, let's go ahead and get those values. So I'm going to go back to A23. So when I plug in things for the reactants, I'm still going to need values for 537, right? Because that's at standard reference state. But now I also need it at the temperature that the reactants are coming in at. And the reactants in that dry air are coming in at 508 degrees Rankine. So, oops, not at carbon dioxide. I just need nitrogen and oxygen. So this value and that value. So I'm going to go ahead and write that on my equation here. Right. So enthalpy of formation for both of them is still 0. But now at 580 degrees Rankine, the enthalpy for oxygen ends up being 40,000. I'm sorry, not 40,000. 4,000. 7.3, and at 537 it's still 3725.1. So same thing we had up here. And well, see, 729.5 is enthalpy at standard reference state for nitrogen. And then at 580 it ends up being 1028.7. I noticed one minor issue. This is 18. It's 18.75, not 18. All right. Man, that was a rough problem. If we plug it all in, let's see what we get. So Q dot over N dot of my fuel, I end up getting negative 1.5, it's 1.582 times 10 to the 6th BTU per pound mole. That's pound mole of fuel, which is C8H18. That's probably another thing I need to fix right here. Oh my goodness. Oh my goodness. Yeah. Let's do another magic trick. Magic. Fixed it. So C8H18. My goodness, guys. All right. I think that I should stop while I'm ahead. So we will work some other problems like this. And yeah. So got problem 7, 8, and we will briefly talk about adiabatic flame temperature, but we probably talk a little bit about it. Okay. So at most, we got 3 problems next time. So hopefully that will go well. All right. Good luck. Hopefully everybody does good on your test and or at least for unit 4, and I will see you in class on Monday. All right. Thank you.